Let's take a look at how to evaluate some antiderivatives. Remembering the power rule for integration, we're going to have to take each variable quantity, add 1 to the exponent, and then divide by that new exponent. And we're going to work one term at a time. We can bring the 5 out in front for the first term. Now we're doing the antiderivative of x to the 4th. So we need to add 1 to the exponent, and then we divide by that new exponent. Now we move to the second term. We'll keep the 8 as the coefficient. We have x to the 4th as we add 1 to the exponent, and then we divide by that new exponent. The 9 remains as our coefficient in the third term. Add 1 to the exponent, divide by the new exponent. Now in the fourth term, remember, of course, the exponent is assumed to be 1. We keep the 2 as the coefficient, and we multiply that by x squared over 2. The last term is assumed to be x to the 0 power, so as you add 1 to the exponent, it becomes x to the first. You could also think of it, considering the fact that derivatives and antiderivatives are inverses of each other. If you were to take the derivative of 7x, you get 7. So you could think of it as, what do I have to take the derivative of to get 7 as my answer? So that's really where 7x comes from. You can think of it as two different ways. Then of course we need plus c, because as you saw in the introductory activity, there could have been a constant term on this original function that when you took the derivative of it, it became 0 and zeroed out. So you need your plus c, your constant of integration, to account for the fact that there could have been a constant term affixed with this function. Now we just simplify. We end up with x to the 5th minus 2x to the 4th plus 3x cubed minus x squared plus 7x plus c. One of the most wonderful things about antiderivatives, and what most people really like about them, you have a way to check your answer. Now that we've arrived at this as our antiderivative, take the derivative of this. You should get your integrand back again. If you don't, you made a mistake. That's something that we never had with derivatives, a way to check our answer. Here we do. So please do take advantage of that. Let's try another one. Now as we go through these, if you think you're getting pretty good at them, please feel free to pause this video, try it on your own, then restart it to see how you did. This is a problem in which we're going to have to algebraically manipulate it. We're going to have to rewrite the square root of x as x to the 1/2 and distribute it across the quantity x plus 1 over x. So if we distribute, we get x to the 3/2 plus x to the negative 1/2, because remember, 1 over x would be x to the negative 1 dx. Remember, we're going to add 1 to our exponent, then divide by that new exponent. Some people find it helpful as they're just starting this out to actually write that out. You get very good at working with fractions in your head. If we add 1 to the exponent of 3/2, we get 5/2. Then we have to divide by 5/2. But if you're dividing by 5/2, remember that's the same as multiplying by the reciprocal of 2/5. So we have 2/5 x to the 5/2 plus adding 1 onto the exponent of negative 1/2, we get a positive 1/2, but then we're dividing by it, so we're multiplying by 2. And then, of course, you need your constant of integration. Again, take your derivative of this. You'll notice you get this integrand of x to the 3/2 plus x to the negative 1/2 back again. Yet another one we'll have to simplify using our laws of exponents. If we have t squared over t to the 4/3 Subtracting the exponents, we get 5t to the 2/3. And then we have 7t to the negative 4/3. We're going to add 1 to our exponents. So the 5, this 5 here, that's going to remain as our coefficient. If we add 1, the 3/3 onto 2/3, we get 5/3. Then we have to divide by it, so we're multiplying by 3/5. Now our 7 remains as our constant. Doing the same with our exponents, we have t to the negative 1/3, but then we're dividing by negative 1/3, so that's multiplying by a negative 3. Plus c for our constant of integration. Simplifying this, we have 3t to the 5/3 minus 21t to the negative 1/3 plus c. Again, feel free to check your answer. I highly suggest that by taking the derivative of your answer and making sure you got your integrand. In our next example, we're doing the antiderivative of 2 over x. Now this is one for which, remember, that would be 2x to the negative 1. The power rule does not work. This is the first of the special rules we looked at. The 2 will remain as our coefficient. Antiderivative of 1 over x, remember, is natural log absolute value of x. Yes, it has to be absolute value. Again, we will talk about y in a later lesson. Plus c. Again, you can check your answer. Derivative of natural log of x is 1 over x, so you do get 2 over x back again when you check your answer. Now another way to write this, if you think of your laws of logarithms, remember that 2 could pop back up to become the exponent of x. So another way you could write this would be the natural log of x squared plus c. When you square that value, that is the absolute value, of course it's always going to be positive anyway. So that's why you can lose the absolute value bar. So this would be another way you could express your answer. And finally, our last example. We're doing antiderivative of 8 to the x. This was another one of the special rules for you to memorize. It's going to be 8 to the x divided by natural log of 8 plus c. Let's go ahead and check this one to make sure it's right. So if we took the derivative of this, remember 1 over natural log of 8 remains because it's a numerical quantity. Now we're just doing derivative of 8 to the x, which would be 8 to the x, natural log of 8. The derivative of that constant, of course, would just be 0. Notice how your natural logs cancel, and all you're left with is your 8 to the x.